Hello, welcome to Dubeke Consult. And today we'll be looking at a very important structural component known as our beams. Knowing fully well that our beams are charged with the responsibilities of accepting both our walls and our floor loads, and in turn transfer these loads to the columns, which in turn distribute to the foundation. There are key and important parameters that need to be set up before you can take on any beam design. And after you've done your beam design, there are also key and important checks that need to be made in order to have an effectively designed beam. In the course of this video, we'll be looking at the various design options available for us in Prota-Structure, and we also get to look at how we can design our beams to resist what we call the torsional moment. If you find this video helpful at any point, do not forget to like it and subscribe to our channel. Also, you can turn on the notification bell so anytime we post new videos on our channel, you get notified instantly. Hello, welcome to Dubeke Consult, and today we'll be looking at how we can design our beams on this very model. So we've been working on this structure for a while, and today we'll get to see how we can design all the beams on this very structure. So if you agree with me that our beams are structural elements that accept our floor loads, accept the loads coming from the slabs, and also accept the loads coming from the walls, and these loads are transferred from the beams directly to the columns, which in turn transfer to the foundation. So these beams has to be properly designed in order to accept this load that are coming from our slabs or other elements that are on our floors. Okay, so the first check you have to make before going ahead to design your beams is ensuring you've performed a slab design for the respective stories. So you have to ensure that your slab has been designed and also the appropriate reinforcement has been provided, since it is accepting the loads that are coming from this slab before transferring to the columns. So this has been designed from the very first story and other stories. Okay, so once this check has been done, the next step is going ahead to select your preferred reinforcement you intend to use for the design of your beams. So to select this reinforcement, what we'll do is we'll come to the analysis tab and we'll click on our building analysis, and under this building analysis we'll come to edit materials over here, and under the edit materials we'll look for our concrete beams. Okay, so we'll first select our FCU or our grade of concrete, and we'll be designing this with grade 25/30, and we'll look at our grade of steel as well. So let's apply this to every other structural concrete members. So we'll also look at our grade of steel and we'll stick with grade 410. Then we'll now select our rebar diameters we intend to use for the design of our structural beams. So I will unselect all of this and I will start with a diameter of y16. I'll also select a rebar diameter of y20, and for worst case I'll be going with y25. Okay, so these are the three preferred rebar diameter I intend to use for the design of this very structure. So I will come over here to click OK, and I will click OK. So before heading on to our design, let's make another check, which is our building model check, because whatever you have modeled is what will be transferred to the analysis and design phase. So if there is any error on your model, then this error will be carried over towards the design of your beams. So to do that, we'll come to the analysis phase and we'll run a quick building model check. Okay, so a previous analysis has been done for this very structure due to the fact that the slab has been designed, but we still have to run a building model check to check for our beams. So let's start this. And as you can see, the numbers of errors we have on this very model is actually 0. Okay, so we can close this up and we can close this tab up. Okay, so to access our design panel for our beams, you come over to concrete design and you come to beam reinforcement design and you click on our story beams. So this is in case you have rib beams on this structure, or this is in case we are designing for foundation beams. But in this case we are heading over to story beams. So as you can see on the design tab of these story beams, we have all these parts marked as X, which indicates no design has been done for these beams. And from the story 1 up to the 2 up to the last story, we have not designed for any beams. So before we go ahead to design our beams, there are some important settings we need to make. What you don't have to forget is your software is garbage in and garbage out. It only provides you the tool, but it will never teach you how to design. So there are some important settings that we need to make modifications to, so we also probably understand their effects and how it will be considered in the design of our beams. So we'll head on over here to settings and parameters. So the first modification we'll be making at this point, or the first check we'll be doing here, is our concrete cover. So our concrete cover is set to 0 mm from the top of our beam to the bottom and also to the side. Okay, so we have 0 mm set here. But if we leave this at 0 mm, a concrete cover of 25 mm will be adopted in the design of these beams. If you intend to change this from 25 mm to 30 mm, you can go ahead and edit this, probably 40 mm. It all depends on the width of your beam and what you intend to achieve. Okay, but in this case we'll be leaving this as 0 mm, so it automatically adopts a concrete cover of 25 mm, making proper reference to our code of design, which is our BS8110. So after this, we'll come to the parameters tab, and we have different parameters to set up at this very point. The first parameter we have over here is our minimum steel bar diameter, which is the minimum reinforcement size we intend to use for our design. So prior to this point, we selected three different reinforcement, which was Y16, 20 and 25. So our minimum automatically becomes Y16 and our maximum will be Y25. Then we have two more type of reinforcement to specify their diameters over here, which is our web steel bar diameter and our hanger bar diameter. So to proper understand this, so if we cut a section through our beam, you will agree with me that this is most likely the typical arrangement of our beam reinforcement. We have the top reinforcements or our top bars provided at this top zone. Then we have our bottom reinforcement provided at the compression zone. So we also have what our links or our shear reinforcement. So when we are talking about our web bar, we are talking about the reinforcement that is provided away from this flange area, which is coming to this web area. Okay, so what is the minimum reinforcement diameter we intend to use if the beam requires some web reinforcement? Then also speaking about the hanger bars, if we cut a section through a continuous beam, you will agree with me that we'll have a beam moment section that looks just like this. So we'll be having what our maximum moment at the bottom here, our positive moment here, and we'll be having our negative hugging moment at this support zone. So in essence, a higher number of reinforcements will be provided here because of the moment that is active here is maximum at the bottom. Why a higher number of reinforcements should be provided here? Because the hugging moment is the maximum moment at the support zone. same as this and continues this way. So the question is, what happens at this very zone where our beam experiences less moment? Okay, because the hugging moment at this span zone, at this area, will be very minimal. It can even be negligible. So in this case, we can provide what our hanger bars. So we can provide a lesser diameter of reinforcement that is different from this, having little or no moment at the span zone. When we are talking about this top area, okay, we'll be having little or no moment. So in cases like this, we can provide our minimum hanger bar, and this minimum hanger bar will also help us to resist or provide proper resistance to our shear force. Because if we take out this reinforcement at this zone, you will observe that because it's not experiencing maximum moment there, you will observe that these beams or these links here will be left flapping. Okay, so we have to provide what a minimum reinforcement in order to keep these links in shape and also help in shear resistance. Okay, so if we come back to this part, we can choose, we will leave the web steel bar diameter as y16 where we require our web reinforcement, and our hanger bars will put a total of two numbers of hanger bars as minimum, one to the right of our links and one to the left of our links, and the minimum hanger bar diameter is y6. We will use y16. So we can go back and select a different reinforcement size like y12 since it is not really experiencing maximum moment. But to maintain uniformity in our reinforcement, we will leave this at y16. Okay, so for this part is based on our code of practice, so we'll leave this at the default. This is the maximum, or this is the total length of our reinforcement, which is always 12 meters. You can choose to modify this if your country of residence, probably you have a lesser length of reinforcement. Some countries we have 11 meters, some cases 11.5, 11.8. So you can choose to modify this. Okay, now the next modification I'll be doing at this point is our links diameter. So our links, will be selecting y10 as the minimum and maximum, and the link spacing, the minimum spacing between our links, we will keep this at 100 millimeter, and it will range between 100 millimeter to 300 millimeter as the maximum spacings between our links. So we'll go ahead and save these settings, and now we can design our beams. So to design our beams, we'll come to this part here, which is our beam design batch mode, and we'll click here. And when we click this part, you will observe that we have what, three different options available for us to design with. So these first two options are very useful when you are dealing with cases of redesign. Let's say you've performed a previous analysis on a previous design on the structure in question, and some reinforcements were provided. Then probably you made some modifications to what has been provided by the software, or let's say you made modification to the loading on the structure, and now you need to carry out a new design. So you can instruct the software to select a new reinforcement if the previous reinforcement that was designed for is insufficient. Okay, so it will help you to reselect reinforcement in that case. But if you don't want it, let's say you are okay with the reinforcement in the beam and more load was added to that very beam, but you want it to design with that same reinforcement. If it passes, it will show you that it passes. If it fails, it fails. Then after it fails, you can now make modification to the beams yourself. You can go with this option. This is actually the preferred option. But in cases where you've not done any previous analysis or any previous design on the structure in question, just like in this case, it is always advisable you select reselect all bars. So this reselect all bar option will redesign everything afresh. Okay, so we'll select this option and we'll click on calculate. So you give it a few seconds to load. Now our design has been completed, and as you can see, this part has automatically changed to green. So let's close this up. And there are some things you have to pay attention to, because the software has provided reinforcement. It doesn't mean you just have to pack that reinforcement into your detailed drawing. You have to investigate, know what is going on the structure, know what is going on the beam, know what is going on with the reinforcement, and probably make modifications to the reinforcement or the beam thickness where you are not satisfied. Okay, so the first thing we'll be looking at here is our U ratio, otherwise known as our utilization ratio. So this is the capacity of your beam as compared to the load it is experiencing, or as compared to the load that is acting on it. And let's look for one specific beam to further interact with. So let's pick this beam having a utilization ratio of 97%, and we'll open this up to know what is going on with this beam. So as you can see, we have what reinforcements provided in this beam. And to better understand these reinforcements, let's detail this drawing. So if we detail this drawing and we take a study around it, you will observe that we have one, two, three, we have four beams on this very section. Okay, this is a continuous beam having four different sections of beams, while we have at intermediate section we have five numbers of columns, which are 1, 2, 3, 4 and 5. So we have four beams and five columns. Okay, and their respective reinforcement has been provided. So we'll come back to this, but the first check we want to make on this very phase is what? Our deflection check. So let's check the deflection of each of these beam. It is if it satisfy our limit. So for the first section of our beam, we have our deflection. Here is the tab for our deflection. So we have our L over D as 8.08, which is way lesser than the maximum deflection, or the allowable, which is what? 56.95. So we have 8.08 less than 56.95, which is acceptable by all standards. And this is the second deflection check for this other span of the beam. So we have 9.38 lesser than 48.94, same as this, and this is also lesser than 56.93. So this beam actually satisfy our deflection check. And the next thing we need to properly observe is the reinforcement in these beams. Okay, so if you observe at this point, we have two Y16 here at the top, because this part here represents our top bars, while this other part represents what? Our bottom reinforcement. So if you go back to detail this drawing, you will observe that on this beam, at this point we have what? 2Y16 at the top, and at this part we have what? 2Y16 at the bottom. And do not forget that this is at what? The span. Okay, this is at the span. So moving away from our span where our beams are experiencing a sagging moment, to the support area where our beams are experiencing the hugging moment, you will see that the reinforcement that is provided at this top zone has been modified from two numbers of Y16 up to two numbers of Y20. Okay, and after this support area, moving on to the next span zone, which is experiencing our compression. Okay, which is experiencing compressive forces. So you will see that our reinforcement here has been modified to two numbers of Y16, which is actually our minimum hanger bar that was selected earlier. So if we close this and we look at the moment diagram of this very beam, you will observe that the maximum positive moment we have here, which was used for the design of our area of steel here, you will see that we have the maximum positive moment as 38.162, which is at the span zone. Then moving up from this span to this part, we now have what? A hugging moment, and the maximum here is negative 95. So this is the part where we have 4y16, and the minimum hanger bar that was provided at this top zone, because it experiences minimal moment, is actually 2y16. So moving away from the 2y16, the reinforcement that will be able to counter this moment effectively, which is our, I think, 2y20, was provided at this very point, separate from the 2y16. So this is how you can relate this to the reinforcements that has been provided by the design software. But we'll be making some modifications to this, and this is actually being designed, this is actually being checked under the envelope load case. So always ensure you are checking under this envelope load case. You can also see the effect or the moment on your beams on the different load cases, okay? But the envelope design is what is being, the envelope diagram is what is being used for your design. So let's close this up and come back to our beam, so we can further relate that here a minimum hanger bar has been provided, okay? Because the required AS, or the area of steel required at this point, is 18.63 millimeters square, which is way minimal. But at the bottom zone, the area of steel required is 202.28, okay? Hence 2y16 is satisfactory. But moving from this span zone on to this support zone, we have 2y20 provided here, because our required area of steel here is 511.08 as the maximum. We have 373 here coming from the left hand side, and we have 511 coming from the right hand side, okay? So while you are checking this reinforcement, there is an important parameter here you should be paying close attention to, which is our extra AS. So our extra AS is speaking to the extra area of steel provided above what is required to satisfy the moment that is acting at each of this zone. It could be at the top zone, it could be at the bottom zone, okay? So this part is the extra area of steel provided against what is needed, and this other part is also the what area of steel provided at the top against what is required, okay? So to further understand this, let's bring out our steel table and see how these values came about. So if we bring out our steel table and we also bring out our calculator, and we look at this part here, you will see that our required area of steel, let's start with this part experiencing a sagging moment. You will see that our required area of steel at this bottom, okay, you will see that this part is what? 202.28. So what has been provided for the bottom zone is what? 2y16. And if we trace two numbers of y16 on our steel table, we have what? A area of 402 millimeters square. So if we type this 402, do not forget that this is always an approximate value, okay? I know it's about 402 point something or 401 point something, but this is an approximate value. So if we take this 402 and we subtract from what is required, okay, if we subtract 202.28, we have 199.72. So if you also observe the bottom part of our extra area of steel provided, you will see we have 199.84, which is related to 199.72. So this is just due to the approximation of this very steel table, okay? So this is what has been provided above what is required. And if you also look at this part, you will see that we have what? 511.08 as the maximum area of steel required at this top zone. So if look at the reinforcement provided here, it was provided two numbers of what? Y20. So if you also trace down two numbers of Y20, we will have area of steel of 628 millimeter square. So if you have this 628 and we subtract this 628 from the area of steel required, we should be having, which is 511.08, we should be having 166.92, which is closer to 117.24 at this very top zone. So this is the extra that has been was provided, and the difference between this and this is just due to the approximated value. Okay, so you always have to check this value and try your best to always ensure this does not go below 100 millimeter square, because if we take down this value, if we take this to two numbers of y16, you will see that we are owing the required area of steel. So in this case, it has not even been able to provide the reinforcement for us. We are still owing. So in order to maintain a uniform reinforcement, I would prefer we design this top zone with steel y16. But what we can do is reduce the numbers, reduce the steel by diameter, but increase the number. So if we take this to three numbers of y16, you will see we've satisfied the red part that we have here. We've satisfied this, and the extra that has been provided above what is required is 94.15 millimeter square. Okay, so this is how you can relate your values in your beam design. Also, to maintain a uniform reinforcement diameter across this beam, we can as well reduce the diameter of this reinforcement to y16, but we can increase the number. Okay, so let's increase this number until it satisfy our requirements. So even at 3y16, we are still lagging behind. So let's take this to four numbers of y16. So this has been updated to four numbers of y16, and the extra provided is 199.91 at the left and 214.22 at the right, which is way above 100 millimeter square and is actually very satisfactory. But if you observe something, when we took this from three numbers of y16, or just observe this part. Okay, if we take this from three numbers in order to satisfy this as required, so this, you will observe that this other part here turns to red. Okay, so if you trace this to this part, you will see the label here as S bar top. So your S bar top or your S bar bottom, so the S bar top is for the spacings between your reinforcement at the top, while your S bar bottom is the spaces between your reinforcement at the bottom. And this is a very crucial and important parameter, because this helps you to manage the spaces between your reinforcement. So let's detail this drawing, and that part should be the second support zone, which is this. Okay, so if you look at this part, this is the part we are referring to having four numbers of y16, and if you look at the section label, this is y10 in brackets and 7. So if we come here to y10 and 7, this is the four numbers of y16 that has been provided at the top, and this is the two numbers of y16 at the bottom. So the S bar top is speaking about the spaces between this reinforcement at the top zone. So do not forget that your reinforced concrete beam does not only comprise of your reinforcement, it comprises of both your reinforcement and your concrete. And in your concrete, you have both your fine aggregate and your coarse aggregate. So you have to maintain a decent spacing between this reinforcement in order to accept the coarse aggregate size that will be used in the construction of this beam. Okay, so if these reinforcements are closely spaced, then you'll be having a challenge of putting your concrete or your coarse aggregate into this beam, and this can in turn lead to honeycomb on your structure. So it's advisable to know your coarse aggregate size you intend to use for construction, which is always at, let's say, a maximum of 20 millimeter. And this coarse aggregate size, you also have to give it some allowance, because not all the coarse aggregate size will be 20 millimeter, some will get to 21, some 20. So it's always advisable to keep the spaces between your reinforcement as a maximum of 25 millimeter. Okay, so that it will accept that coarse aggregate, and in turn it will not cause honeycomb on your structure. So let's close this, and you can observe the spacing between the reinforcement at this top zone to be 35 millimeter. So coming back to this point, let's see how they were able to come about this value here. If we pick up our calculator, and remember what we are concerned about is the spacing between this reinforcement that will accept our coarse aggregate. So if we pick up this calculator and we try to understand what is going on with this beam, you will see that the width of this beam is 230 millimeters. Okay, so the width is 230 millimeters. So out of this width, to get this spacing, we will be taking out the concrete cover at the left, at the right, and also the concrete cover at the left. Okay, so the concrete cover, prior to this stage, we adopted a concrete cover of 25 millimeter. So if we take out 25 millimeter from this part, and we also take out 25 millimeter from this part, we'll be having a total of 50 millimeter. Okay, so if we subtract 230, if you just subtract 50 from 230 millimeter, we'll be having 180 millimeter. So one more thing that is taking up the spaces in this very beam is our links. And if you observe here, we have what our links as y10. So we have our links on the right and we have our links on the left. So if we take out these links both on the right and the left, we will have a total of 20 millimeter. So if we subtract 20 from 180, then we are left with spacing of 160 millimeter. Now we have what total numbers of what four numbers of y16. So this is also taking up the space left for our coarse aggregate to get into this beam, or our concrete in question to get into this beam. So the value here is 160, and if we multiply 4 by the diameter of our reinforcement, which is 16, we have what 64. So if we take out 160, or if we take out 64 from 160, we are left with what 96 millimeter. Now this 96 millimeter, we will be having a spacing of 1, 2, 3, because these are now the accepted spaces to receive our concrete. So if we divide this by these three numbers of spacing in between our reinforcement, if we divide this by 3, then we have what 32. So it means the maximum coarse aggregate size will be 32 millimeter. But it is advisable to keep this, or your coarse aggregate size, you keep this at 20 millimeter, because do not forget that you also have to pass your concrete up to the part where we have what our concrete cover. Okay, so this is actually satisfactory because 32 millimeter is way above 20 millimeter. So we can choose to ignore this part in red because we have 32 here, and it will actually accept what our coarse aggregate. So let's take a look at this other part. What if we have a situations like this? Let's say the reinforcement required to satisfy the moment at this very zone is 4 numbers of y20. Okay, if you observe this air spacing at the bottom, you will see that this has been reduced to 26.7. and if you pick up our calculator as well, and considering a width of 230 millimeter, subtracted from, or we subtract concrete cover of 25 from left and right, which is 50, and we also subtract the links diameter from the left and right, which is 20, and the 4 numbers of y20, if we multiply this, we will be having 80 millimeter. So if we subtract 80 millimeter from this, now we are left with what 80 millimeter. So the spaces between them will also be 3 different spaces. So if we divide this by 3, then we are having what 26.67, which is approximately 26.7. So this will accept a maximum, or since this is above 20 millimeter, which is the quartz aggregate size, we can also choose to ignore this very error. Okay, then the question is, what happens when we can no longer uh, ignore this error? Let's say we are having five numbers of y25. Let's say we're having five numbers of y25, and the spaces between those reinforcement has turned to 8.8 millimeter, which is way below our aggregate size. So if we take a look at this detailed drawing, that part, you will see we have what, 5y25 at this very point. So the spaces between them, you can see, is way minimal. So if we are casting, or if we are concreting this beam, it will be difficult to pass our concrete to this other zone, okay, because the spaces here are too small. So in essence, this place is prone to honeycombs. So what can we do when we have situations like this? Because your area of steel is your area of steel. Your area of steel required is your area of steel required. You must have to satisfy it in order to sleep well. So you must have to provide the area of steel that will satisfy what the area of steel required. So what happens when we have situations like this? If we have situations like this, what we can do is create a different layer of reinforcement which is separate from the first layer. So we have what, bottom bar here, and if you observe this part, we also have what, another layer of bottom bar. So we can come here to this second part and reduce this, and since five numbers of y25 is required, we can reduce this to three numbers, come to the second layer and take this what to two numbers of what, y25. Now if you detail this, you will see that we'll still be having the same issue. Okay, we'll still be having this. So what you will do is, after increasing this to two numbers and reducing this to three numbers of y25, you come here and take this to your reinforcement at layer 2. Okay, so it will take this to the reinforcement at the second layer. So now when we come back to detail this drawing and we'll come to this part, you will see we have what, 3y25 provided at the bottom layer 1, which is the B1, and an additional two numbers of y25 provided at the bottom layer 2. So we have the strength, or we have the area of steel required satisfied, and we also have the spaces between our the spaces between our reinforcement satisfied in order to receive our concrete. Okay, so let's close this and we'll take this out. Let's take this out and return this to the previous reinforcement diameters and numbers. So do not forget that your software is garbage in and garbage out. Whatever you give to your software is what it will in turn give to you. There is another modification we can make to this structure in order to avoid some errors, and that is related to the detailing as well. So if you detail this drawing and if you observe the reinforcement provided on these beams, you will see that we have what, 2y16 here. Then moving to this part, we have what, 3y16. Okay, then after this support zone, we have what, another 2y16. So what happens when you are not the one constructing on site, you are not managing the artisans on site, or probably you as a structural engineer, you are not detailing this drawing, and you send this to a detailer and he decides to cut just one section through this beam. And if you agree with me, if we cut just a section through this beam, we'll be looking at only this part. Okay, if we cut just this section, which is y10/12/2, we'll be looking at this very one here and having two numbers of y16 at the top and two numbers of y16 at the bottom. So the other part of this beam will not be catered for, because in this case we have what, four numbers of y16. So what some structural engineers can decide to do in this case in order to minimize errors on site is in errors on site or errors due to detailing is, if we close this, they can select the maximum reinforcement at the top zone, then use this as what a conventional reinforcement all across this top zone. Okay, so the maximum, this one we have what at this top zone we have 2y16, we have 3y16 here. Here is 2y16, here is 4, which is the maximum. We can modify this to 4 numbers of y16 as well, which is also the max. So the maximum at the top zone is what, 4y16, while the maximum at the bottom zone is 2y16. So we can modify this reinforcement in order to suit all of these beams. So from this first beam up to the last beam, it will be all through 4y16. Okay, so this can help to minimize errors, but the challenge with this is it incurs more cost on the construction process, because this reinforcement, let's say this 4y16 was supposedly to be provided just 1.45 meters to the left of this span and 1.5 meters to the right of this span. But if we change everything here to 4 numbers of y16 and we change this to 4y16 and we detail this drawing, you will see that all across this beam we now have what, let's look at this section, we now have 4y16. But this can be useful in cases where you are not sure of the construction, you are not sure of who is going to detail your drawing, because they can choose to cut a section through just one point. Okay, we understand that there will also be a call out here indicating that these other spans are 4y16 or 3y16 or whichever the case may be, but the artisans on site, they better relate with diagrams. Okay, they better relate with sections diagrams other than this call out. I'm just speaking out of experience. They better relate with what, this section. So if you have used a conventional reinforcement all across this span, then you can choose to delete every other section and cut just one section, but be sure it satisfies everything about the top zone. Okay, so in this case, as a structural engineer, you have to select whichever pays you. Okay, but there is something else we would like to do, and which is providing our torsional reinforcement for some specific beams. So if we close this up, and you can make other modifications to any of these beams if you are not satisfied with their outcome using the same process of interactive design. So let's close this up and we'll take a look at the 3D of this structure. Okay, so if you look at the 3D of this structure, if you follow this tutorial series from the very first stage, because we started off at the general arrangement, we move to the modeling, we move to the pre-analysis, the application of wind load, we move to the design of slabs and other components, and now we are currently at the beam design phase. So I will actually leave links in the description to get to those other videos, but this is what I'm concerned about. If you look at this slab, or this part, you observe that we have what, a cantilever slab, and this cantilever slab is supported by our beams. Okay, so let's come back to our plan view and let's try to measure this slab. We have a cantilever slab of 1.2 meter. Okay, this is 1200 millimeter, which translates to 1.2 meters, and the thickness of this slab is 200 millimeters. Okay, which is actually supported by the beams. And if you are familiar with structural arrangements like this, considering the fact that this is a 1.2 meter slab, a 1.2 meter cantilever slab, and this is having what, a thickness of 200 millimeter, with these properties, and when load is being applied on this slab, it will cause a twisting effect on this supporting beam. Okay, It will cause a twisting effect on this supporting beam when load is applied on this slab, thereby generating a torsional moment on our beams. Okay, so it means this beam is a critical beam and it has to be designed to resist this torsional moment. So we'll check the properties of this beam and check if the reinforcement that can counter this torsional effect has been provided. If it has not, then we can do this manually. So these are some of the modifications you have to make as a structural engineer, understanding structural behaviors and structural patterns. Remember, the software will never teach you how to design. Okay, it will only give you the tool to design with, but the principles on design, or how structures behave, how structures deflect, that is solely to you as a structural engineer. So what I'll do is I'll come to this plan view, and let's start from the story one. So we have this cantilever on all the stories, having 200 thickness and 1.2 meter cantilevered length. Okay, so this is the supporting beam here, and this is also the supporting beam at this very point. So we have the cantilever here and here. So if you observe the name of this beam, this is 1B20, and this other beam should be, let's see, this is 1B23. Okay, so we'll look at the reinforcement of these two beams, and since this beam is on the same axis, it will be combined together as a continuous beam. So we can select any of them. Let's select this, then we'll right click and we'll come to look at the beam section design, and this is the provided reinforcement for this beam. So let's detail this drawing and see what is going on. So as you can see, we have what for the first beam, which is 1B23. Okay, for the beam which is 1B23, the section is y1 and 2. So let's look at this. This is y1 and 2. So it has provided what two numbers of y16 at the top and two numbers of y16 at the bottom. But do not forget that this is supporting what a 200 millimeter thick cantilever slab, which will cause a twisting effect on this beam. Okay, so in order to resist this effect, we have to provide some web reinforcement in order to counter the torsional moments that this will experience. So what the software is concerned about at this very point is to resist the maximum moment coming from the top and the maximum moment coming from the bottom. So this is the modification that you yourself as a structural engineer have to do with your proper understanding of structural behaviors. Okay, so what I will do is I will close this, and in order to provide those reinforcements at those zones, what we can do is we'll come to the web, and remember we've selected a previous reinforcement diameter for our web. So we'll look for the beam in question, which is 1B23, and the last one, which is 1B20. Okay, so we'll come to the web zone of this reinforcement, and we can add one y16 here, and let's see what comes out. So as you can see, we've provided one y16 in order to resist that torsional effect. But I don't really feel satisfied with just one numbers of y16, considering that the thickness of this beam is also 600 millimeter, which is almost going to a deep beam. Okay, so what I will do is I will come back here and I will increase this to two numbers of y16, and I will come to the last beam as well, which is 1B20, and I will take this to two numbers of y16. So for these other beams, I can leave it as it is, but because of the peculiarity of these two end beams, we have to make this very modification. So let's detail our drawing and see what comes out. So now we have what 2y16 provided as the web zone, and this will also help in providing additional stiffness. Okay, it will help to provide more shear resistance to these beams. So this is okay
for these other beams that are not connected to the cantilever, we can leave this at 2y at the provided reinforcement just at the top and the bottom zone. But for this, we have to provide what our torsional reinforcement or our web reinforcement. So we can close this and save the modified reinforcement for this very beam. So we can go ahead and do this for this beam and this as well for all other stories, but due to time, we'll be terminating these lectures at this very point, so you can make this effect on every other stories. So these are some of the modifications you have to make, and if you found this video helpful at any point, do not forget to like it, subscribe to our channel, and turn on the notification bell so anytime we post new videos on our channel, you can get notified instantly. To know how we were able to get to this level, I'll leave a clear video, a clear link of all the stages in the description of this very video. So thank you, and see you in the next series.